Hey guys, welcome back. Now you know the key characteristics of big data. It is now time to understand the challenges or problems that come with big data sets. So in this lesson, let's take a sample big data problem, analyze it, and see how we can arrive at a solution together. Ready? Imagine you work at one of the major exchanges like New York Stock Exchange or NASDAQ. One morning, someone from your risk department stops by your desk and asks you to calculate the maximum closing price of every stock symbol that is ever traded in the exchange since inception. Also assume the size of the dataset you were given is 1 terabyte. So your dataset would look like this. So each line in this dataset is an information about a stock for a given date. Immediately, the business user who gave this problem asks you for an ETA on when he can expect the results. Wow, there is a lot to think here. So you ask him to give you some time and you start to work. What would be your next steps? You have two things to figure out. The first one is storage and second one is computation. Let's talk about storage first. So your workstation has only 20 GB of free space, but the size of the data set is 1 terabyte. So you go to your storage team and ask them to copy the data set to a NAS server or even a SAN server. NAS stands for Network Attached Storage and SAN stands for Storage Area Network. So once the dataset is copied, you ask them to give you the location of the dataset. So a NAS or a SAN is connected to your network, so any computer with access to the network can access the data, providing if they have permission to see the data. So far good. The data is stored and you have access to the data. Now you set out to solve the next problem, which is computation. You're a Java programmer, so you wrote an optimized Java program to parse the data set and perform the computation. Everything looks good and you're now ready to execute the program against the data set. You realize it's already noon. The business user who gave you this request stopped by for an ETA. That's an interesting question, isn't it? So you start to think, what is the ETA for this whole operation to complete? And you come up with the result set. For the program to work on the dataset, first the dataset needs to be copied from the storage to the working memory or RAM. So how long does it take to copy a 1 terabyte dataset from storage? Let's take our traditional hard disk drive. That is the one that is connected to a laptop or workstation, etc., right? HDDs, or hard disk drive, have magnetic platters in which the data is stored. When you request to read data, the head in the hard disk first positions itself on the platter and start transferring the data from the platter to the head. The speed in which the data is transferred from the platter to the head is called the data access rate. This is very important, so listen carefully, right? Average data access rates in HDDs is usually about 122 megabytes per second. So if you do the math, to read a 1 terabyte file from a hard disk drive, you need 2 hours and 22 minutes. Wow. Now that is for a HDD that is connected to your workstation. When you transfer a file from a NAS server or from your SAN even, right? You should know the transfer rate of the hard disk drives in the NAS servers. For now, we will assume it is same as the regular HDD, which is 122 megabytes per second. And hence it would take 2 hours and 22 minutes. Now what about the computation time? Since you have not executed the program yet, at least once, you cannot say for sure. Plus, your data comes from a storage server that is attached to the network. So you have to consider the network bandwidth also. So with all that in mind, you give him an ETA of about 3 hours. But it could be easily over 3 hours since you're not sure about the computation time. Your business user is so shocked to hear 3 hours for an ETA. So he asks the next question. Can we get it sooner than 3 hours? Say maybe in 30 minutes? You know there is no way you can execute the results in 30 minutes. Of course, the business cannot wait for 3 hours, especially in finance where time is money, right? So let's work this problem together. How can we calculate the result in less than 30 minutes? Let's break this down. Majority of the time you spend in calculating the result set will be attributed to two tasks. First is transferring the data from storage or hard disk drive, which is about 2.5 hours. And the second task is the computation time, right? That is the time to perform the actual calculation by your program. Let's say it's going to take about 60 minutes. It could be more or it could be less. I have a crazy idea. What if we replace HDD by SSD? SSD stands for solid state drives. SSDs are very powerful alternative for HDD. SSD does not have magnetic platters or heads. They do not have any moving components and it's based on flash memory. So it is extremely fast. Sounds great. So why don't we use SSD in place of HDD? By doing that, we can significantly reduce the time it would take to read the data from the storage. But here's the problem. SSD comes with a price. They're usually 5 to 6 times in price than your regular HDD. Although the price continues to go down, given the data volume that we are talking about with respect to big data, it is not a viable option right now. So for now, we are stuck with hard disk drives. Let's talk about how we can reduce the computation time. Hypothetically, we think the program will take 60 minutes to complete. Also assume your program is already optimized for execution. So what can be done next? Any ideas? I have a crazy idea. How about dividing the 1 terabyte data set into 100 equal sized chunks or blocks and have 100 computers or 100 nodes do the computation parallelly? In theory, this means you cut the data access rate by a factor of 100 and also the computation time by a factor of 100. So with this idea, you can bring the data access time to less than 2 minutes and computation time in less than 1 minute. So that sounds great. It is a promising idea, so let's explore even further. There are a couple of issues here. If you have more than one chunk of your data set stored in the same hard drive, you cannot get a true parallel read because there is only one head in your hard disk which does the actual read. But for the sake of the argument, let's assume you get a true parallel read, which means you have 100 nodes trying to read data at the same time. Now, assuming the data can be read parallelly, you will now have 100 times 122 megabytes per second of data flowing through the network. Imagine this. What would happen when each one of your family member at home starts to stream their favorite TV show or movie at the same time using a single internet connection at your home? It would result in a very poor streaming experience with a lot of buffering. No one in the family can enjoy their show, right? What you have essentially done is choked up your network. The download speed requested by each one of the devices combinedly exceeded the download speed offered by the internet connection, resulting in a poor service. This is exactly what will happen here when 100 nodes try to transfer the data over the network at the same time. So how can we solve this? Why do we have to rely on a storage which is attached to the network? Why don't we bring the data closer to the computation? That is, why don't we store the data locally in each node's hard disk? So you would store block 1 of data in node 1, block 2 of data in node 2, etc. Something like this. Now we can achieve a true parallel read on all 100 nodes. And also we have eliminated the network bandwidth issue. Perfect. That's a significant improvement to our design, right? Now let's talk about something which is very important. How many of you have suffered data loss due to a hard disk failure? I myself have suffered twice. It is not a fun situation, right? I'm sure most of you at least once faced a hard drive failure. So, how can you protect your data from hard disk failure or data corruption, etc.? Let's take an example. Let's say you have a photo of your loved ones and you treasure that picture. In your mind, there is no way you can lose that picture. How would you protect it? You would keep copies of your picture in different places, right? Maybe one in your personal laptop, one copy in Picasa, one copy in your external hard drive. You get the idea. So if your laptop crashes, you can still get that picture from Picasa or your external hard drive. So let's do this. Why don't we copy each block of data to 2 more nodes? In other words, we can replicate the block in 2 more nodes. So in total, we have 3 copies of each block. Take a look at this. Node 1 has block 1, 7, and 10. Node 2 has blocks 7, 11, and 42. Node 3 has blocks 1, 7, and 10. So if block 1 is unavailable in node 2 due to a hard disk failure or corruption in the block, it can be easily fetched from node 3. So this means that node 1, 2, and 3 must have access to one another. And they should be connected in a network, right? Conceptually, this is great, but there are some challenges implementing it. Let's think about this. How does node 1 knows that node 3 has block 1? And who decides block 7, for instance, should be stored in node 1, 2, and 3? First of all, who will break the 1 terabyte into 100 blocks? So as you can see, this solution doesn't look that easy, isn't it? And that's just the storage part of it. Computation brings other challenges. Node 1 can only compute the maximum close price from just block 1. Similarly, node 2 can only compute the maximum close price from block 2. This brings up a problem because, for example, data for stock GE can be in block 1 and can also be in block 2 and could also be on block 82, for instance, right? So you have to consolidate the result from all the nodes together to compute the final result. So who's going to coordinate all that? The solution we are proposing is distributed computing. And as we are seeing, there are several complexities involved in implementing the solution, both at the storage layer and also at the computation layer. The answer to all these open questions and complexities is Hadoop. Hadoop offers a framework for distributed computing. So Hadoop has 2 core components, HDFS and MapReduce. HDFS stands for Hadoop Distributed File System, and it takes care of all your storage-related complexities like splitting your dataset into blocks, replicating each block to more than one node, and also keep track of which block is stored on which node, etc. MapReduce is a programming model, and Hadoop implements MapReduce, and it takes care of all the computational complexities. So Hadoop framework takes care of bringing all the intermediate results from every single node to offer a consolidated output. So what is Hadoop? Hadoop is a framework for distributed processing of large data sets across clusters of commodity computers. The last 2 words in the definition is what makes Hadoop even more special. Commodity computers. That means all the 100 nodes that we have in the cluster does not have to have any specialized hardware. They are enterprise-grade server nodes with a processor, hard disk, and RAM in each of them. That's it. There is nothing more special about them. But don't confuse commodity computers with cheap hardware. Commodity computers mean inexpensive hardware and not cheap hardware. Now you know what Hadoop is and how it can offer an efficient solution to your maximum close price problem against a 1 terabyte dataset. Now you can go back to the business and propose Hadoop to solve the problem and to achieve the execution time that your users are expecting. But if you propose a 100-node cluster to your business, expect to get some crazy looks. But that's the beauty of Hadoop. You don't need to have a 100-node cluster. We have seen successful Hadoop production environments from small 10-node cluster all the way to 100 to 1,000-node cluster. You can simply even start with a 10-node cluster, and if you want to reduce the execution time even further, all you have to do is add more nodes to your cluster. That's simple. In other words, Hadoop will horizontally scale. So now, you know what is Hadoop, and conceptually how it solves the problem of big datasets. With that, let's wrap this lesson and move on to the next lesson.